Hello everybody. I'm sorry that I can't be with you in person. I've decided to make a little video to introduce simulation and crystal ball specifically since I can't be in class. Sorry that this is a little bit funny technologically. I'm having some issues with the software, but hopefully it'll work well enough. Let's start up where we left off. Recall before spring break we talked about risk analysis, uncertainty and sensitivity analysis, and the whole objective of these methods is to really study the extent to which assumptions that we make in the model, whether they're structural assumptions, the equations and the structure of the model, or they're values that we assign to input parameters, we want to know the extent to which changing those assumptions and input parameter values can change our outcomes that we care about, whether we're calculating the expected profit of a service line expansion or trying to choose between alternatives in a decision analysis problem. We want to know whether changing assumptions and changing input parameter values might change dramatically or not the outcomes that we're calculating or the decisions that we're trying to make using the model. So we talked about a couple of approaches for conducting risk analysis. One of them being best case, worst case analysis. And what we did there essentially was we came up with two scenarios, a best case and a worst case. And in the best case, you want to go through and think about what are all the values, the input parameter values that we don't know for sure, and what is the best case. In the best case, what value would each of them take on? Worst case analysis, we do the same thing for each of the uncertain, unknown input parameters. We think about, okay, what's the worst case? In the worst case, what's the value that each would take on? If you plug those into the model, calculate your outcomes, you can get a sense of what's likely to happen in the best and the worst case, respectively. That's great information, but it's often not enough. So what if analysis allowed us to construct other scenarios, not just the best case and worst case, but scenarios that are in the middle? We could do lots of things with these scenarios. This is truly what if analysis is quite unconstrained. You can change only one input parameter at a time, multiple input parameters at a time, but what you're doing is you're asking about a bunch of what if questions. What if our input parameters that we don't know took on these set of values that you specify? Plug those into the model, calculate the outcomes, record the outcomes somewhere, and then start over again with a new scenario that you want to simulate. An example of how we did that was the data tables. So recall that what we did, we had a model. In this case, it was a decision tree model, and it was the model essentially took our assumptions about what was contributing to our cost estimates. In this case, we wanted to provide some service. I think it was transportation, and we were trying to decide if we should hire 3 or 4 staff. And there were a bunch of things we didn't know. For example, we didn't know how many patients would come in, and depending on how many patients came in, how many hours of staff time would be needed. And so we laid out this decision tree to try to help us process information about the alternatives, our choices, our decisions, and the states of nature that might occur. And we used this tree to try to better understand the likely cost, the expected cost, with different states of nature. So we built data tables, to try to understand how variation in 2, we had to pick 2, the 2 we picked are listed here in orange and yellow, 2 input parameter values. If we allowed them to change, the values to change over ranges that we specified, what we would do with data tables is essentially fill these tables with outcomes that we care about documenting with the model. So what we're doing is essentially in data tables is using Excel to help us easily simulate 48 different scenarios. So this is what if analysis. We're simulating 48 different scenarios. We're plugging into the model essentially using Excel and data tables 48 combinations of these the values of these 2 input parameters. We plug what Excel does when we create a data table is essentially plugs in the value, so in the column and the row, and obtains the expected cost in the top table and the optimal decision alternative to hire 3 or 4 employees in the bottom table. So I'm documenting 2 outcomes here, and it records. It plugs in all 48 combinations of the 2 input parameters that I tell it to, and it records the outcomes that I care about. So this is what if analysis, where instead of simulating 2 scenarios like we do with best and worst case analysis, we're simulating 48. We're asking what if these 2 input parameters took on all these different combinations of values. And you could create data tables for other input parameters that you think are unknown and explore the impact of varying them on outcomes that we care about. But the limitation of data tables, while they're really great and they can help us neatly process this information in a two-dimensional table, the downside is we're limited to at most looking at two different inputs, varying two inputs at a time. So it can get hard to interpret this if we say had 3 or 4 or even more input parameter values that we didn't know for sure. So that's where simulation comes in. Simulation, think of simulation as an extension of data tables and what-if analysis. It's all it really is. The goal is really to try to understand the distribution of possible results, outcomes that we care about, from a model when the values for the uncertain input parameters are drawn from their plausible distributions. So what we're doing is we're asking a whole bunch of additional what-if questions, simulating a bunch of different scenarios. In fact, what we're going to do is we're going to specify distributions that characterize the uncertainty around our input parameters. The simulation software, which will be doing for us essentially what data tables did for us with only 2 input parameters, will plug in, it'll draw values for each of the uncertain input parameters, plug them into the model, calculate the outcomes, record them, and then start over. Repeat a bunch of times, say 1,000 times. We would run the model 1,000 times. We would call these replications or simulations. We're running the model 1,000 times, plugging in different values for our input parameters, and documenting or recording the results, the outcomes that we care about, and we can have more than one. At the end of this, we've got a lot of information about the different values that the outcome variables take on. So in data tables, we had 48 different outcomes, 2 different outcomes in the 2 different tables. With simulation, we can have more than 2 outcomes and more than 48 replications of the model. You can have more than that with data tables too, but the data tables will get bigger. And then, once we get all of this information about the possible values that your outcomes take on, we can process it using statistical analyses, just basic descriptive statistics, like we might calculate the mean, the expected value, the average value of each of the outcomes. We might care about the minimum and maximum for each. We might want to calculate the standard deviation to get a sense of the variation. Is there a big spread? Is there a lot of variation in the outcomes, or are they pretty tightly centered around the mean? There are a lot of different descriptive statistics that we might want to use to describe the variation in the outcomes that we care about using simulation. So let me talk just quickly about this process. We're going to use Crystal Ball. It's another add-on to Excel, and it will help us. Again, it helps us do what data tables does if we're just varying 2 input parameters at a time. Crystal Ball allows us to vary many, many more at one time. And really, Crystal Ball is just keeping track of all of this. It's helping us draw values from the distributions around the input parameters, plugging them into the model, recording the outcomes of interest, and helping us calculate some basic descriptive statistics on the outcomes. So the process really starts with what we've been doing all semester long, defining the problem that we want to study and building the base case model to help us translate our inputs and our assumptions into calculating the outcomes that we want to calculate to help us make a decision. And just so you're not surprised, that will remain the most time-consuming and most challenging part of this whole process. Simulation, trying to understand how uncertainty affects your outcomes of interest, that's actually the easy part. We'll practice doing that a bunch of times in this module, but the hard part will remain building the models that are sort of the foundation of the simulation analysis. The models that we are going to plug in different values for the uncertain input parameters in. So, first step, define the problem. Second step, build a base case model. This is all the same. But then the next step is we look back at this model that we've built to calculate the outcomes of interest, and we think about, okay, which of these are random variables? Which input parameters are random, are unknown, or have some distribution? We might know values that each might take on, but we don't know for sure what that value is going to be in each point in time or each context in which we need to estimate demand or whatever it is. So think about what are the input parameters, the independent variables that we don't know for sure. And then any output or outcome or dependent variable that is calculated based on those independent variables is also random then. So if you're calculating an outcome and it depends on, or it's a function of, some uncertain input parameter, we would describe that outcome then as random as well. So you want to think about which are the uncertain or random input parameters and what then are the uncertain output variables that are calculated as a function of those input parameters. So identify them. The next step is to assign a distribution. I talk about this as characterizing the randomness in the input parameters. We want to be able to describe the possible values that each of these input parameters that are uncertain come from. So I want you to think about things like the expected value. So what's your best guess of the input parameter that is unknown? If it's demand, in a demand for physical therapy services in a given month, what would you expect that value to be? Is it 80? Is it 100? Is it 3,000? What would you expect that input parameter value to be? And then how much variation would you expect there to be over time? Or if you were to sample that value in different cities, how much variation do you expect there to be? A little bit? If your expected value is 80, is the variation small and that input parameter is not likely to vary much beyond 70 to 90? Or is it big? If the expected value is 80, is that input parameter actually likely to vary between 20 and 140? So how much variation do we expect there to be in the input parameter that we don't know? And then what's the shape of the distribution? This will make more sense when I show you some pictures in a couple minutes. So we want to describe, and we'll talk about how to do this, but I want you to describe the shape of possible values that each of these input parameters might take on. Crystal Ball is going to use that information to help you sample from these distributions to plug in different scenarios into the model. The next thing we want to do is specify the dependent outcome cells. Again, this is really linked to the third bullet down where we identified the random variables. Here it's just telling Crystal Ball what are the dependent or outcome cells that we want Crystal Ball to keep track of for us. The next step is that we want to determine the number of iterations or replications, runs of the model, scenarios that we want to simulate in the model. With the data table example, we had 48. We plugged in 48 different combinations of our two input parameters. With Crystal Ball, we want to often run more iterations. As the book tells us, many more. The more iterations we run, the more information we have about the outcome variables. But the more iterations we run, the longer it takes Crystal Ball to do this. So there's this trade-off between time. If your model happens to be quite big, it can take a lot of time, and the amount of information you have. I would encourage you to run a lot of iterations. Your models are going to run pretty fast, so try to run about 1,000. And then the last bullet, we run the simulation model. Crystal Ball will help us capture values of the outcome variables that we care about, but then we need to interpret the results. We need to be able to say something about all of that information that Crystal Ball captures about the outcome variables across the different replications. Again, using descriptive statistics. What's the mean? What's the variance? What's the min and max? That sort of thing here. Let's pause and go to a next video just so that this isn't going to be too hard for you to stream.